part 1 of section 9.3, sequences. We are going to start by introducing some new terminology and then using some of this new terminology to define what a sequence is and how we use them algebraically. So let's start with our definitions. So we are talking first about infinite sequences. So we have two types of sequences that we look at. The first type is a finite sequence, and then we can use that to define an infinite sequence. So a finite sequence is an ordered progression of numbers that has a finite number of terms. Now, an infinite sequence is a function. It is a function that assigns a unique number that we will call a sub n to each natural number k. Now, when we say natural number, we're talking about our counting numbers. So we're going to be working on the sequence is an ordered set of numbers. So when we count things that are ordered, we count 1, 2, 3. So we won't have any negative k's. We won't have any decimals or fractions. So we have the first term, the second term, the third term, such as that. Okay, now there's two ways to define these. One is recursively and the other is explicitly. So recursively defined function is one that has a formula that relates the terms to the previous terms. That would be to say something like start at the number 4 and add 3 every time. So you're starting with a number and you're given a way to find the next one based on the last one. So 4, then 7, then 10. That's recursively defined. Some of you may be familiar with the Fibonacci sequence. That's a recursively defined one. You take the first two terms and you add them together. So you're given 1 and 2. The next one is 3, then 5, and so on like that. So you always add the previous two terms to get the next one. So that's a recursively defined sequence. An explicitly defined one is when you're given a formula that tells you exactly how to find any term in the sequence, the first term, the 50th term, without having to know any of the other ones. So that's when the terms are defined as a function. And we'll just use that k again without knowing the previous terms. Okay, a couple examples one where we're going to use a recursive formula and one where we're going to use an explicit formula. So the first example is number 1 on page 656, and that is going to be an explicit formula. So we are to find the first 6 terms and the 100th term. And the formula we're given is A sub n equals n plus 1 over n. So all we have to do is substitute in our counting number starting at 1 for n, and we can find each of the 6 terms. So our first term, which would be a sub 1, is going to equal 1 plus 1 over 1, which is 2. A sub 2, replacing n, will be 2 plus 1 over 2, which is 3/2. A sub 3 will be 3 plus 1 over 3, which will be 4/3. A sub 4 will be 4 plus 1 over 4, which will be 5/4. A sub 6 is going to equal, whoops, I skipped 5. A sub 5 is going to be 5 plus 1 over 5, which is 6/5. And a sub 6 is going to be 6 plus 1 over 6, which will be 7/6. And of course we need the 100th term. And a sub 100 is going to be 100 plus 1 over 100, which will be 101 over 100. So that's why it's called explicit, because you can find any term without having to know a specific term because you're given a formula. Now number 5, on the other hand, on the same page, says to find the first 4 terms and the 8th term. Now we have to be given some information. So we are given that a sub 1 is 8, and we can find any term, a sub n, by taking the 1 before it, which is defined as n minus 1, like that, and subtracting 4. And we're also told that this is only good for n's greater than or equal to 2, which makes sense because you have to know the first term to get the previous one. Okay, so we already know a1, so we can find a2. Is going to be a1 minus 4, so that's going to be 8 minus 4, which is 4. And then a3 is going to be a2 minus 4, so that's going to be 4 minus 4, which is 0. And a4 is going to be the previous term, a3 minus 4. So 0 minus 4, which is negative 4. Now to get to 8, we're going to have to keep going. So we're going to have to keep subtracting 4. So let me just put these in a set together here. So far we have 8, 4, 0, negative 4. And I could just keep subtracting 4 every time. So then I have negative 8, negative 12, 1, 2, 3, 4, 5, 6, negative 16, and then of course the 8th term is negative 20, and then I put a dot, dot, dot to show that my sequence continues. So I can write out here that a sub 8 equals negative 20 if I want to be very specific. All right, so the next thing we're going to talk about is limits. Limits of infinite sequences. So we're going to first define what the limit of an infinite sequence is. So we're going to let a sub n in a set like that be a sequence of real numbers and consider the limit as n approaches infinity of a sub n. I'm going to consider that limit. So if the limit is a finite number, we'll call it L, the sequence converges. So we can say the limit of the sequence is 10. So it converges. Because all the terms together, if you look at them, are approaching the same number. So they might be like, 6, 7, 8, 12, 15, and then they go 15.2, 15.8, 15.9, 15.95. So they're approaching a number which is 16. So that's what it means by converges. And the finite number. So, and that number L is the limit of the sequence. Okay? So, if it doesn't converge, if the limit is infinite, or non-existent, the sequence diverges. Okay, so using that, this becomes important because you're going to see there's going to be some functions that are hard to define in terms of a nicely laid out function. But if you can write it as a sequence, then you can talk about its behavior. So that's why the limit's important, because the limit talks about behavior at very large or very small values. Okay, so looking at a couple of examples here. So in number 13, we're to determine whether the sequence converges or diverges. I don't know why my pen's skipping today. And then if it converges, give the limit. And you can see we're going to be able to use some of the information that we've learned this year to help us determine the limit. Okay, so this sequence is defined this way. You have 1 over 1, and then you have 1 over 4, 1 over 9, 1 over 16, dot, dot, dot. So you have to come up with the explicit form for that. And this one's kind of easy. You can see the top's always going to be 1. If you look at the numbers in the denominator, they're all perfect squares. So, oops, sorry. It's going to be n squared, 1 over n squared. So what we're going to do is we are going to take the limit as n approaches infinity of 1 over n squared. And so what we have is, there's two ways to look at this. What we have is a number that's getting larger and larger quickly because we're squaring it, and we have 1 over it. So if you take a look at the value of the function, like 1 over 6 compared to the 1 over 10 billion, that's going to be such a tiny number, it's going to approach 0. And we can also use our rational expression limits. So we have an exponent in the denominator, which is larger than 1 in the numerator. So the limit is going to go to 0. This is like looking at your horizontal asymptote. So we know now that the sequence converges because it's a real number. 0 is a real number. And we know that that limit is 0. Okay, we'll do one more of those. So again, we're going to determine, let me move this up first. We are going to determine whether the sequence converges or diverges. And give its limit. And this time they give us an explicitly defined function, not function, sequence. So we have 3n minus 1 over 2 minus 3n. So what we're going to do is we're going to take the limit as n approaches infinity of our 3n minus 1 over 2 minus 3n. And when we do that, what we're going to see is that the degrees are the same in the numerator and denominator. We have a 1 here and a 1 there. So we can take the ratio of their leading coefficients. So we're going to have a 3 over a negative 3. So we get negative 1. So the sequence converges. To negative 1. So we'll stop there, and in the second part of this video, we will finish our lesson.